This lecture looks at RC circuits, that are circuits with resistors and capacitors. A capacitor stores charge and electrical energy on conductive surfaces that are near one another, for example parallel plates, as shown below. There you see plus charges on one side of the plate, minus charges on the other plate. As you go from one side of the capacitor to the other, there is a voltage change or a change in potential energy. If you were to short the two sides of the plate by connecting a wire from one side to the other, when you short the capacitor, the charges will flow until they're equally distributed and there's no longer any voltage or potential energy. Of course, the short releases energy very quickly. The capacitor might blow up if you were to short a capacitor. It's not a wise idea to short a capacitor. The charge held on a capacitor is equal to the capacitance times the voltage across the capacitor, delta V. Capacitance C is a measure of the charge the capacitor can hold. It depends upon the geometry and materials of which the capacitor is made of. The units of capacitance are farads, and the symbol in a circuit looks like a parallel capacitor. If you don't want a capacitor to blow up when you take charge off of it or current off of it, we use a resistor to limit the flow of current into and out of a capacitor. It turns out that the product of the resistance times the capacitance sets the time scale. Sometimes this is known as the RC time constant. R times C turns out to be have units of seconds. Let's look at how we charge and discharge a capacitor. First, we look at charging a discharged capacitor, a capacitor that has no charge upon it. Here we have a portion of a charging circuit which has a resistance with a resistance R and a capacitor with a capacitance of C. We put a battery across that open part of the circuit and immediately a current starts to flow. The current will start out high with an initial value and fall to some zero as time goes on. The exact form of the curve that the current follows is equal to an initial value of the current, which is the voltage divided by the resistance, times a decaying exponential. The charge follows a slightly different curve because it starts at zero, there's no charge in the capacitor. As a function of time it rises and comes to some constant value, and that constant value is equal to the capacitance times the voltage, and the full time dependence of the charge is shown by this curve and also by this equation. If we look at discharging a capacitor, there again we have a portion of a circuit with a resistor and a capacitor. Now we just put a short across this capacitor and resistor, so the current immediately starts to flow through the resistor. The current is flowing in the opposite direction, so we're going to call it a negative current. It starts out with a large negative value, and as a function of time it goes to zero. So the equation will have a form of some minus times the initial voltage divided by R, that'll be the current, times again a decaying exponential, and it has that sort of shape. The charge will start out high and then fall as a function of time, and the equation has the form of Q of t is equal to C times V, the capacitance times the voltage, that's the initial value of the charge, times the decaying exponential. And again you have this form. Notice that RC is the time constant in the exponential. It determines how fast the exponential decays. Now let's take a look at an example of what I call a battery substitute. Sometimes a capacitor is used instead of a backup battery in an electronic device. How does this work? A large capacitor can provide a source of current while the power is off. If you discharge a large capacitor through a large resistor, it can take a long time before the current and voltage drop significantly. So you have a discharge circuit with a capacitor that's fully charged, waiting for the power to go off. When the power goes off, a switch is flipped and current starts to flow through whatever circuit we might need to power. How long will it take till the current falls to 90% of its initial value? We'll take the capacitance equal to 1 farad, the resistance equal to 1 kilo ohm or 1,000 ohms, and assume that the capacitor is charged to a voltage of around 3 volts. We have our solution for the current as a function of time for a discharging capacitor, which is equal to the initial value of the current, which is equal to minus V divided by R times the decaying exponential. At time equal to 0, we have the initial value, and if we plug in our values for voltage and resistance, we have 3 volts divided by 1,000 ohms negative, which is equal to minus 0.003 amps or 3 milliamps. At a time when the current has fallen to 90% of its original value, that means the current is equal to minus 0.027 amps, which we got by multiplying 0.003 times 0.9, 90%. Or this also can be written as minus 0.003 amps times the decaying exponential at the time t sub 90% divided by RC. RC, if we multiply it out, ends up being 1,000 seconds, so that's our time constant. If we divide back, we find the original value divided by the 90% value divided by the original value, you get, of course, 0.9 or 90%, and that's equal to just this decaying exponential. We can solve for the time for 90% by putting in natural logs on both sides. Then the natural log of the left side gives you minus 0.105. The natural log of an exponential just brings out the argument of the exponential. And solving that for t 90% is equal to 105 seconds. So that it will take 105 seconds before the capacitor drops, the current drops to 90% of its original value.